I welcome all to the session 32 on current electricity in BSc third semester as prescribed by Karnataka University, Dharwad. Today in this session, I am dealing with expression for magnetic field on the axis of the circular coil carrying electric current and discussion of special cases. Outcome of this session are mention of expression for magnetic field on the axis of the circular coil carrying electric current and discussion of special cases like magnetic field at the center of the circular coil and magnetic field due to a small circular coil. Let us discuss on the expression for magnetic field on the axis of the current carrying circular coil. Consider a circular coil of radius A, center O and current I flowing through the coil in the anti-clockwise direction. Consider P as the point on the axis of the coil at a distance x from the center O. At point P, we have to calculate the magnetic field. Consider a small current element dl at the point A at a distance r from the point P. The magnetic field at the point P due to the current element dl at A is given by dB is equivalent to mu naught upon 4 pi I dl sine theta divided by r square. Here the current element dl and the line joining the point A and P both are perpendicular to each other. So the angle theta is equal to 90 degree. Substituting theta equal to 90 in the above equation, we get dB is equivalent to mu naught upon 4 pi I dl divided by r square. The direction of the magnetic field produced here due to the current element dl is perpendicular to the line AP. It is represented in the figure by dB bar, which is along PC. This magnetic field dB bar is making an angle phi with the vertical, that is PY. So we have to resolve this dB bar into two components, that is dB cos phi along PY and dB sin phi along Px. Similarly, if we consider a current element at the point B, the magnetic field produced by the current element at the point B at point P is along dB dash, that is along PD. Here this dB dash is making an angle phi with the vertical again. So dB dash is resolved into two components, that is dB dash cos phi along Py dash and dB dash sin phi along Px. Here dB cos phi and dB dash cos phi are equal and opposite to one another. So they cancel one another. So the total field at the point P is due to the two horizontal components, that is dB sin phi and dB dash sin phi both together gives the total magnetic field at the point P as 2 dB sin phi. Here, if we substitute the value of dB, we get 2 times mu naught I divided by 4 pi dl sin phi divided by r square. Solving the equation for the entire coil, the magnetic induction at the point P is given by B is equivalent to mu naught I a square divided by 2 times a square plus x square the whole bracket raised to 3 by 2. If the coil contains n number of turns, then the magnetic field B is given by mu naught Ni a square divided by 2 times a square plus x square raised to 3 by 2. Unit of magnetic field is Tesla. We further discussed the special cases wherein the magnetic field induced at the center of the circular coil. So, at the center, x is equivalent to 0. If we substitute x equal to 0 in the equation for B, we get the equation as mu naught Ni a square divided by 2 times a square plus 0 square raised to 3 by 2, which can be simplified as mu naught Ni divided by 2a. Magnetic field due to the small circular coil. Small circular coil means the radius is much smaller as compared to the distance on the axis we have considered. So here for the small coil we have x greater than a. Hence the equation can be written as B is equivalent to mu naught Ni a square divided by 2x cube. The references for this session are Electricity and Magnetism by Satya Prakash and S. Chance, Electricity and Magnetism by R. Murugesan. Thank you.